In this video, we solve problem 12.4.018 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the principal unit normal vector at the specified value of the parameter. And we're given this vector valued function r of t. It has components 2 or square root of 2 times t, e to the t and e to the negative t. I will write this vector function in component form like this. Now we're asked to find the principal unit normal vector. Now there are a couple of ways that we could find that. I highly recommend using the method that I'll use in this video. You can use the definition. The definition of the principal unit normal vector is that n hat is t hat prime divided by the magnitude of t hat prime. But that is computationally intensive. So I recommend not using this. I recommend doing what we're about to do instead. Here is the general approach. If you have an acceleration vector, it can be written as a sub t times t hat plus a sub n times n hat. So it'll have one component in the direction of motion and another component parallel to n hat. And if you add those together, you'll get your acceleration vector back. Now in other videos, we talked about the derivation for a sub t. That's the tangential component of acceleration. You can think of it as the projection of a or the acceleration vector onto t hat. Turns out to be equal to the dot product of a with t hat. It's the signed projection of a onto t hat. And this dot product without an absolute value gives you the appropriate sign. If a and t hat, or if this component of a and t hat point in the same direction, a sub t would be positive. And if a goes in sort of the opposite direction, so that angle between the acceleration and the unit tangent is obtuse, then this dot product would be negative and a sub t would give you the right value. So you take that t hat and you'd multiply it by a negative number and you'd have a component for a that's over here, which is what we would expect. So we'll use this formula to find a sub t. We'll use the Pythagorean theorem to find a sub n. This side length squared plus this side length squared equals that side length squared. So we'll have a sub t squared plus a sub n squared equals the magnitude of a squared. And we can ignore this t hat and n hat because they're 1 unit long. Like the length of this vector is just the absolute value of a sub t. And the length of this vector is the absolute value of a sub n. So that squared plus that squared will equal that hypotenuse squared by the Pythagorean theorem. Because we have this formula, we can solve for a sub t. And because we know how to find the acceleration pretty easily just by taking the second derivative of position, we can find the magnitude of the acceleration vector. So 2 of these are known. There's 1 unknown. You can solve for a sub n by subtracting this from both sides and taking the square root. And we get this. So these are the formulas that I would recommend using. We'll compute a and t, and then we'll compute a sub t. Once we've got a sub t, then we'll use the Pythagorean theorem to find a sub n. So we'll use this formula. And then once we've got a sub t, a sub n, t hat, and a, and we needed t hat and a to find this first one. So we'll have all of these pieces here except for n hat. We'll solve for n hat. N hat will be the acceleration vector minus its tangential vector component divided by the magnitude of that normal component. So we'll get the unit vector that is pointing in the direction that we're turning. So that's the plan. I'm just going to go through and compute each of these guys. But to compute this one, we need acceleration and the unit tangent vector. So we'll start with that. My r of t can be written this way in component form. R prime just comes from taking the derivative component by component. Derivative of a constant times t is just the constant. Derivative of e to the t is e to the t. Over here, when I take the derivative, I've got a function inside another function. Derivative of e to some power is e to that power times the derivative of the inside by the chain rule. The derivative of a constant times t is just my constant, which in this case is -1. That's our prime. Our double prime comes from taking the derivative of that again. Derivative of a constant is 0. Derivative of e to the t is e to the t. When we take the derivative again, well, we'll end up multiplying by another -1 by the chain rule. Negative times a negative will make that a positive. So this is our acceleration vector in general, but we want the acceleration vector at time t equals 0. We're going to evaluate all of these at time t equals 0. So we will find that now just by evaluating all of our components at t equals 0, and of course simplifying. E to the 0 is 1, and the opposite of 0 is 0. So we've got a vector with components 0, 1, and 1. So we computed r prime, we computed the acceleration vector, which is r double prime, and then we computed a of 0. Okay, now I need t hat. Now remember, t hat is the unit tangent vector, so I take a tangent vector, which is r prime, or the velocity vector, and I divide by the magnitude of the velocity, which is the speed. It's going to give me the direction that we're moving, provided that r represents a position function. So I'm trying to get to t hat. In order to find t hat, and I'm interested in it at t equals 0, I will next find r prime of 0. So that will give me the tangent vector at t equals 0. Again, just replacing t with 0. And then simplifying. E to the 0 is 1. And now we want to take this vector and we want to divide, or we want to divide it by its magnitude. So now before we do that, we'll find the magnitude of the vector by taking the components, squaring them, adding them, and then taking the square root. So we'll have 2 plus 1 plus 1, square root of 4, which is 2. So t hat at 0 is r prime at 0, that vector divided by the scalar, its magnitude. And we're just putting these two pieces together that we just computed. Taking this guy and we're dividing by 2. So I'll just take the components and I'll divide each of them by 2. All right, that's t hat at 0. Now, a sub t, that's the tangential component of acceleration, is the dot product of the acceleration with t hat. I want a sub t at 0. So I'll find a sub t at 0 by taking these two guys and dotting them. So I've got the vector with components 0, 1, and 1, and I've got this vector. And we're taking a dot product. And I'm just dropping the dependence on as t, lowercase t, and just saying that, but remember we're evaluating everything at t equals 0. When we compute a dot product, you take the components, you multiply and add. So we'll do this times this, and then we'll add this times this, and then we'll add, and this times this, and then we'll add. I've got 0 times something, plus 1 times something, plus 1 times something. And I have 0, turns out to be 0, plus 1/2 minus 1/2, happens to be 0. All right, so the tangential component of acceleration is 0. That means we're not speeding up or slowing down in that tangential direction, or that, the tangential tangent, we're not speeding up or slowing down tangent to the curve in the direction of motion. So that means all of our acceleration is leading us to turn. That's interesting. Okay, well, with that in mind, a sub n is really easy to find. If this is 0, then a sub n is just the magnitude of our vector a. It's the square root of the magnitude of a squared. Since this is 0, we're just going to get the magnitude of a. That happens to be 0 for this particular curve. Now our vector A at time t equals 0 had components 0, 1, and 1. So we'll just find the magnitude of that now. Take the components, square them and add them, and take the square root. 1 plus 1 is 2, so we've got the square root of 2 there. Alrighty. And then n hat is our acceleration minus the tangential component of acceleration divided by a sub n. But the tangential component of acceleration is 0 because a sub t is 0. So we're just going to take our acceleration vector and divide by a sub n. So in general, I would have this. Well, in general, for lowercase t equals 0, I'd have this. This vector is the vector with components 0, 1, and 1, and then I have 0 times something. Doesn't even matter what that vector is because 0 times that vector is going to be the 0 vector divided by the square root of 2. So I'm basically just taking my acceleration and dividing it by square root of 2. So I have the vector with components 0 and 1 over square root of 2 and 1 over square root of 2. And that is n hat at time t equals 0. So we can write our answer that way if we want to. I prefer component form, as you can tell if you've worked through my videos or seen my examples. But if you prefer to write your answer in terms of I hat, j hat, and k hat, you can say this is 0 times I hat, which is of course 0, plus 1 over square root of 2 times j hat, plus 1 over square root of 2 times k hat. And that's exactly the same thing as that. I highly recommend using these formulas rather than using this definition because these are computationally simple. And I like them too because they're physically meaningful. They tell us whether we're speeding up or slowing down, if we're turning. And it's all very simple. It's all based on this little right triangle over here, which is pretty cool. Please let me know if you have any questions.